Welcome everyone to this video. We are going to begin the topic of fluid dynamics in this video. Basically, fluid dynamics means that with respect to stationary container or a stationary pipe-like thing, the fluid has started traversing. That is, we see that the fluid particles are in motion uh, with respect to their container or with respect to some hollow object through which they can flow. So, fluid dynamics encompasses in itself a lot of terminology. One of the first terminologies which we learn is velocity. So, what do we mean by velocity of fluid particles? The velocity of fluid particles is simply the simple velocity which we see and observe in real time. As the fluid particles are moving, they also travel some distance, they cover some displacement per unit time. So they have some path on which they move. So first we learn in fluid dynamics is steady flow. So what does steady flow mean? Steady flow means that the flow of the fluid as it is happening currently in the pipe or in the uh, whatever thing which we are observing, like the small pitted tube or venturimeter, it is not changing with time. So uh, when the change happens in the fluid, uh, uh, not with respect to time, then that is kind of a steady flow. Opposite to that is called unsteady flow. So we'll say fluid does not, or fluid flow does not change with time. Similarly, unsteady flow. Fluid does, or fluid flow does change with time. Right. So there's one example. If we want to take an example of unsteady flow, so if it is the first thing which we do, uh, mostly in the morning when we wake up, uh, one of the first activities which we do is brushing our teeth. So in that particular activity, we turn on the flow of the tap. So when we are turning the tap or we are pushing some button, we are basically activating some kind of mechanism which increases the flow of the water through some orifice. So that increase of flow is unsteady. That is a classic example of unsteady flow. Then, as you are hearing the sounds which are being held, which are being created by the bandwalas outside, how can that help us in understanding the dynamic flow? So there is flow of particles in air as well. The air particles which are moving towards and away from each other, they are moving with increasing velocity. That is with speed of sound. So as the wave travels through the speed of sound, we say there is some certain flow of that particular sound towards us. And that speed is nearly some 343 meters per second, which is like pretty high, right? So it does not matter if the like the sound is created right next to us, or whether the sound is creating like 100 meters away from us. The sound is going to reach us in that particular fraction of a second. And let's say if I breathe and that information is passed on to some, let's say, stranger, and that person is able to create a sound, how much time would that sound take to be heard by me? That is also part of a flow, right? How does the air flow from one point to another? Right? Pretty interesting thing. And how would we analyze if, let's say, uh, we are sitting in a car, right? So when a car is, let's say, running, we know that the engines in the car is getting the fuel which we are supplying uh, through the uh, carburetor and so on, other oil filters and so on, so many devices. What is the flow rate through those devices? So all that comes in fluid dynamics. Now, next idea is turbulent flow. Turbulent flow is basically when we say we have some kind of a pipe, and in that pipe, the flow of particles is not uh, a uniform flow. That is, the particles are basically traveling in random direction at different points of space. That is, this particle is traveling in some this path, this particle is traveling in some this path, some particles are traveling in a circular path. So there is no regularity of paths through which they are traveling. So this also happens in case of heart attacks when the fluid flow is blockaged through some kind of artery. So there is a turbulent flow of blood through that particular section. Otherwise, there is relatively smooth flow, or we say relatively um, steady flow of the blood. Next, we want to basically start with the idea of continuity equation. So let's begin. So equation of continuity helps us decide that how much amount of fluid is entering a particular section of a pipe and how much amount of fluid is going to leave that particular pipe. A pretty interesting thing. So we have some kind of section here. So this is the fluid, how the fluid flows, right? So as the fluid is flowing from one point to another, we will say that this fluid is some V1, this fluid velocity is some V2. So our objective is to determine what is the relation between V1 and V2, right? So we say that, let's say at this particular section, some X length of fluid enters our pipe here, somewhat like this, right? Some delta X length of fluid is entering here. Okay. Similarly, uh, similarly we'll say some delta x2 length of pipe is leaving the particular section over here, right? So this V1 is equal to delta X upon some T time taken by the pipe, by the fluid to enter this particular pipe or cross section area, where the cross section area mean is this. So this whole section of the fluid is entering this cross section area in T time. So this V1 is delta X by T. Similarly, this V2 is going to be delta X2 upon T. So delta X1 is some length, right? So we want that how much mass of fluid is entering inside the pipe and how much fluid is leaving the pipe. So next we have uh, the same section which we are considering. What is the volume entering section 1? So we need a cross section area of this particular section, section 1. Cross section area is let's say some capital A. And here the cross section area is some small a. So you see cross section area capital A into V1 and V2 into the time t. This V1 into T, this is the length of the fluid entering the section here. So this length into cross section area gives us the volume. Volume multiplied by density gives us mass. So let's say density of the fluid here is rho1. Its density can change because of some circumstances. Maybe we are adding some heat. So here the density is rho1. It will be equal to the mass of the fluid leaving here. So it would be rho2. Cross section area small a, speed v2, and time taken t. So that's what we have done here. So when we cancel out everything, we'll get rho 1a v1 is equal to rho 2a v2. So times t time cancels out. So this is the case of steady flow. That means that in t time we are considering some amount of fluid is entering and same amount of fluid is exiting this particular section. And after that, we'll assume that the density of the fluids entering and leaving this particular pipe is same. So the equation becomes AV1 is equal to AV2. So this is our equation of quantum. So today we are going to do only this much only, not a lot of lectures. So in the next lecture, we'll be starting with the idea that what is Bernoulli's theorem. So that is also one of the terms which I was referring. That Bernoulli theorem it has kinetic energy per unit volume. What is the speed or what is the energy associated with the fluid as it is moving? Uh, because of its motion, it will have energy. So how is that energy useful for us? When we apply pressure on the fluid or some pressure in the fluid is there at particular section. So how that pressure affects our equations or how is that relevant to the study of fluids? Because we know pressure is some important quantity. If a fluid has high pressure, it is likely to expand the a pipe in which it is existing. Although the pipes today which we use are or it would depend upon the pipe which we are using that it is able to expand or contract. But that pressure can is a relevant technical quantity. For example, in case of gases are also fluids, although they don't have what we say um, steady flow, right, or streamline flow, which I mean. Streamline flow means that the particles in the fluid they are going like this. So as there is a streamline, in that case, we usually refer to them as liquids. When we have gases, they don't have any kind of streamline; they flow in general. There also we have this parameter called pressure, which is kind of important. So more on that next time. Thank you.